I concluded in the last video lecture that the annual charge is basically comparing apples and oranges. Some of the record efficiencies are stable efficiencies and some efficiencies are not stable. Furthermore, some of the efficiencies are reported for small lab scale devices with a size of 1 square millimeter, and some are reported for a large 6-inch wafer size solar cell corresponding to an area of 250 square centimeters. This is at least 3 orders of magnitude scale difference between lab scale cells and wafer cells. In this video, I will give the answer to the question what the relation between the record efficiencies and the size of the device is. Therefore, I prefer to present the record efficiencies per technologies as a function of the device size. This is nicely demonstrated in this figure. It demonstrates the level of maturity of a PV technology. A mature technology is a PV technology that has limited loss in conversion efficiencies when going from small lab scale devices to large sized modules. Let's consider the first and the most dominant PV technology, crystalline silicon. The multi-crystalline silicon efficiencies go from 22.3% for 4 square centimeters down to 21.3% for a 6-inch wafer size solar cell, down to 19.9% for 1.5 square meter PV module. From wafer to module, 1.4% is lost. The losses are a result of lower coverage of the active area due to gaps between the solar cells and electrical resistive losses due to the interconnection between the cells. A similar trend can be seen for the IBC HIT technology of Canica. The record efficiency of a cell is 26.7% and decreases slightly to 24.4% for 1.3 square module. This represents a loss of 2.3% from cell to module. Let's consider the 2 PV devices structure for the 3.5 PV technology that have resulted in both lab scale devices and small sized modules. These architectures are the thin film gallium arsenide PV modules from Alta Devices and the indium gallium phosphide gallium arsenide indium gallium arsenide triple junction from Sharp. It can be clearly seen that the negative slope in this plot is larger than for the crystalline silicon technology. This suggests that upscaling of the single and the triple junction device to module size is more challenging. This results in more efficiency losses. In gallium phosphide, gallium arsenide, indium gallium arsenide triple junction module has a size of 858.5 square centimeters, which is about 30 by 30 square centimeter. For such typical small module size, this triple junction has the highest efficiency of all PV technologies. Let's consider the thin film PV technologies, and we first look at thin film silicon PV technology. It's the green line at the bottom. The line hardly has any slope, indicating that the processing of this technology is rather mature. The record lab cell of about 1 square centimeter has a record efficiency of 12.7% and it is based on the amorphous nanocrystalline silicon tandem cell. The module with a size of 1.4 square meters is 4 orders of magnitude larger and has an efficiency of 12.3%. This represents a small loss of only 0.3%. This demonstrates that the processing technology of thin film silicon PV technology is very mature. Thin film silicon processing is, for instance, used for other industrial applications like large display technologies. The disadvantage of this technology is the lower stabilized module efficiency when compared to the other dominant thin film PV technologies like CIGS and cadmium telluride. The CIGS technology shows a 22.6% record efficiency for a cell of 0.4 square centimeters, while Mia-Soli have demonstrated certified module efficiency of 15.7% with a size of almost 1 square meters. This still shows a significant drop of 6.9% of going from cell to module size. An important factor that plays a role is that the various CIGS module manufacturers use different CIGS processing methods. Therefore, the intellectual property needed to reduce the upscaling losses has to be mainly developed in-house. The record efficiency of lab cells and modules based on cadmium telluride are all achieved by the leading company in this technology, First Solar. The record efficiency drops from 21.0% for a lab cell of 1 square centimeter down to 18.6% for a module of 0.7 square meters. This is a relative smaller loss of only 2.4% in reference to the CIGS PV technology. If we look at the emerging technologies that have resulted in small module designs, we see that the single junction organic PV technology goes from an 11.2% for a 1 square centimeter lab cell down to 8.7% for a module of a size of 800 square centimeters. This represents a 2.8 absolute drop, but it represents a 25% relative drop in performance when upscaling from lab scale to module. An additional challenge for the organic PV technology is that these reported efficiencies are not stable. Under operation, the module performance will significantly degrade. The other line is corresponding to the perovskite technologies, which shows that this technology is far from mature yet. Record efficiencies above 20% have been obtained for cells with a size smaller than 1 square centimeter. The conversion efficiencies are drastically reduced when the size of the perovskite cell is scaled up with a factor of only 10 or 100. In addition, the perovskite technology suffers from instability issues as well. The performance degrades in time. So perovskite PV technology still faces significant challenges to prove that it can become a mature PV technology in the future. This figure shows record efficiencies. Are these the same efficiencies as the module efficiencies in mass production? I will discuss that in the next video lecture.